What if I told you that there are places in the universe where the laws of physics no longer behave normally, almost like an anomaly? Nothing familiar, nothing you could imagine. Regions so particular that space and time themselves are deeply warped. The famous black holes. And what if we took a quick journey into the infinitely vast? Black holes are often described as cosmic vacuum cleaners, but that idea is misleading. Their gravity is extreme, yes, but what actually happens near them isn't intuitive at all. Some of the phenomena observed around black holes still remain open questions in physics. So instead of simplifying them, let's take a closer look at what we actually know and what we still don't. First, where do they come from? A black hole forms when a massive star collapses under its own gravity beyond the critical limit. The core compresses into an extremely dense region, often described as a singularity, a point where our current physical models no longer make reliable predictions. Surrounding it is the event horizon, a boundary beyond which nothing can escape, not even light. These ideas are not just theoretical observations of stars orbiting Sagittarius. They provide strong evidence for a supermassive black hole at the center of our galaxy. And to give a sense of scale, the matter falling toward a black hole can release enormous amounts of energy, sometimes comparable to the output of billions of stars. Now imagine moving closer to a black hole, not in a fictional scenario, just following the predictions of modern physics. As you approach the event horizon, time no longer behaves the same way. To a distant observer, your motion would appear to slow down more and more, as if you were gradually freezing in place. But from your own perspective, at first, everything would feel relatively normal. This is a direct consequence of gravitational time dilation, predicted by general relativity. Then, tidal forces begin to matter. This effect, often called spaghettification, would stretch your body along the direction of the gravitational field. From the outside, you would appear elongated. From your perspective, the effect would build progressively, not instantly. Closer still, the environment becomes even more extreme. Light paths curve noticeably. Radiation intensifies. Matter spirals inward in what is known as an accretion disk, heating up to very high temperatures and emitting X-rays and gamma rays. These emissions are measurable and are one of the main ways we detect black holes. At this stage, different observers would strongly disagree on what is happening. Someone far away would see your signals slow down and fade. But locally, your experience would remain continuous. Even your view of the universe would change. Light from distant stars would bend, distort, and concentrate in unusual ways, altering your perception of space itself. At the center lies what we call the singularity. According to current equations, it is a region where density is predicted to become extremely large, and where space and time, as we describe them, stop behaving in a predictable way. However, this is also where our theories are incomplete. We do not yet have a fully consistent description that combines gravity and quantum physics under these conditions. What we do know is that black holes are not just passive objects. They influence their surroundings on a massive scale, shaping the motion of stars, contributing to galaxy formation, and affecting how energy is distributed across the universe. Even without seeing them directly, their presence can be measured through their effects. Black holes are not simply destructive objects or cosmic vacuum cleaners. They are well-supported predictions of modern physics, confirmed by multiple independent observations. At the same time, they expose the limits of our current understanding. They show us that space and time are not fixed backgrounds, but dynamic structures that can be distorted under extreme conditions. And that is what makes them so important, not because they are mysterious, but because they help us understand how the universe actually works. But imagining this scenario raises a more basic question. Before even thinking about black holes, how would a human survive in space at all? Moving, breathing, staying alive, all under physical conditions completely different from those on Earth. That's exactly what we'll explore in the next video.